Kannan Gopalakrishnan. He was working as a senior architect at Engineering Design Research Centre, L&T Construction, India's largest construction company. He's also worked on projects ranging from institutional buildings to international airports, apartment complexes to aircraft hangars. He's also attended 3 international conferences and 2 national conferences, and has also presented technical papers at the Jawaharlal Nehru University, Delhi, and the MSRIT, Bangalore. He's also won the national championship at Archaman at the India's largest architecture quiz. Sir Kannan Gopalakrishnan currently runs a design firm, Habitat Design Studio, and he is also a visiting faculty at the renowned architecture schools in Tamil Nadu.
Welcome back to UGC lecture series. This is AR 6006 Structure and Architecture. We are still covering units 3 and 4. We are doing contemporary structural expression through case studies, and this is lecture 15. If you remember lecture 14, we saw the famous INMOS microprocessor facility designed by Richard Rogers, and in this episode we will be looking at 3 very interesting buildings: the Fleet Guard, PA Technology Center or the PATH Center, Princeton, the Olympic Athletic Center of Athens. We'll straight away move on to Fleet Guard. Located in a newly designated industrial zone within a few kilometers of the town of Quimper in Brittany and adjacent to a major road, the site provides magnificent views across the country towards Quimper on the South Brittany coast. The highly adaptable building, capable of responding to changes and needs and functions, has established the company in mainland Europe. The first look at the building, Fleet Guard, looks like this. It has a striking similarity with the Renault manufacturing facility which we saw earlier and by Norman Foster. Fleet Guard was designed in 1981, whereas Renault Center was designed in 1982. Renault Center was in France and Fleet Guard was in Britain. The first look of the building itself is a white box, but then it doesn't look like a white box because of all the structural things that are jutting out outside. The red colored structural elements on the top and suspended roof steal the attention from the white box which the architect has designed. Fleet Guard specializes in manufacturing heavy duty engine filters, and the new plant at Quimper was to include production of lines for air, fuel and oil filters, storage facilities and administrative headquarters totaling 8,750 square meters, but with a future growth potential of up to 40,000 square meters over 15 years. The design places great emphasis on minimizing intrusion on the landscape. If you could see the building, which is placed in a landscape of a very, very beautiful setting, the building insisted on minimizing the effect on landscape. Another look at the building with its structural elements, and you see there is a man standing right next to it, just so that you can understand the scale of the project. The project is in Brittany, France. The surplus excavated soil that has been used to create a carefully controlled landscaping scheme is famous in this building, relegating across the roads to perimeter of the site and segregating the industrial from personal traffic. A dynamic suspension structure reduces both roof span and structural depth, diminishing the overall mass of the building. The external structure frees the interior roof zone for flexible services distribution, unhindered by the excessive structural depth of a conventional frame of a similar span. In a conventional building, what usually happens is the depth of the structure itself dictates a very, very difficult choice for the structures to pass through all the requirements, but in this case there is an external framework of structure which holds the building roof in place by in the form of cables, which means that there is a lot of space for the structural elements to go in. Here is another look at the buildings and its structural elements. The stairwell is enclosed in glass so that it becomes the focal point internally, linking both physically and visually the production and administrative areas. The main structure consists of elements which require very little fabrication and can be joined simply. The structural connections are necessary for extending the building that can be made without removing existing cladding, thereby avoiding disruption to the use of the building. The total street weight is about 40 kilograms per meter square, about 70% less than conventional structure of comparable base size. The cladding is clearly articulated from structural frame to facilitate bay by bay expansion without disruption to fleet guards' activities, and is separated from the roof zone by a continuous band of high level glazing, bringing natural light to all parts of the building. This is another look at the interior. Again, Richard Rogers is trying to use the same concept of inside out architecture, where he tries to get the service lines onto the visible area of the building. You can see all the visible structure lines, service lines with brightly painted colors. That is a signature inside out style or the high tech architecture style. The Fleet Guard building received famous awards such as these awards. To look at the Fleet Guard building, this is the building with its structural components with respect to the human scale. This is how massive the building bay is. Look at the height of the roof of the building itself, and look at the height of the mast which supports the cables of which in turn supports the whole ceiling. We immediately go on to the next building, which is called the Pat Center. Pat Center is in Princeton, USA. If you ask Richard Rogers about this building, he would say this: if we lose control of the process of building, we become merely decorators of sheds. If we are simply decorators of sheds, we shouldn't be called architects. At first glance, it seems that it is ironic that the architect of this PA Technology Center in Princeton actually said this, because the building looks like this. If you don't call this a decorated shed, what else would you have called this? If you don't use that terminology, what else will you call this building? The Pat Center's 40,000 square foot single story volume is largely unpartitioned and quite shed like inside. Its stayed roof structure, painted bright red and articulated by clevises and stainless steel pins, is certainly an exhibitionist form of ornamentation, if not outright decoration. A more careful reading of the Pat building reveals, however, that this building is more than a simply decorated shed. Here you see those famous things which clevises which Richard Rogers mentions. Again, very similar to the previous Inmos Center, we have a frame and we have all the services kept above the building. Here again you have the street like character, which is now becoming very signature of Richard Rogers. Many aspects of the building, including its structure and air conditioning system, evolved in response to the client's needs or Rogers' ideas about how efficient manufacture, construction and maintenance should happen. As a research and development company specializing in product design and telecommunications, Pat Limited wanted its technology center to be flexible and expandable enough to meet unpredictable space requirements. The unpredictable space requirements gave birth to a space like this. Largely column free space inside, which is supported by an A-frame very similar to the Inmos Center which we saw earlier. Two very large bays with frames which are supported by subordinate structures which still hold the roof from suspended area. It also wanted a building that would be visually expressive of the highly technical operations inside. To solve the problem of spatial uncertainty, Rogers designed the building interior as a single large volume related by a minimum of relocatable partitions. Here again, they wanted the building to be visually expressive of the highly technical operations inside, which means that highly technical operations which are happening inside of the building should be visible outside, which means that there is only one style in operation that offers you that kind of a system, and that is inside out style. And who is famous for that kind of a style? Richard Rogers, yes. And that is why Pat Center called Richard Rogers for its iconic structure. So he can design this building in an inside out fashion and high tech architecture, and thereby clearly getting what they wanted, because they wanted the building to emulate, to show visually, expressively about how technical operations happen inside. At the same time, there were problems of uncertainty in spatial organization in the factory building itself, which Richard Rogers took to task, and how he managed to get that. He made one single large volume which are stayed by A-frames and which are stayed by steel cables. So the one large structure again with modifiable wall panels, and you can change the interior layout like anything. Wherever you want to put anything, you have it. It's very possible. The stayed roof provides a largely column free interior which increases flexibility, and with the exposed HVAC equipment and translucent facade panels provides the building's high-tech expression. Close up look at structure and MEP services of the building. Look at how vibrantly colored paint which are used on the structure and service elements. The building's articulated structural components reflect the design as a kit of parts pre-manufactured from off-the-shelf products. Kit of parts technology is something which Rogers made very famous, because Rogers wanted buildings to be like this. You want to build a building, so you go to a store, then you order certain parts, very similar to how you assemble a furniture kit or something, very similar to how you assemble Lego blocks. You order certain blocks, you fit it, and then you get it. So a building is a kit bag of various parts for him. That is the famous kit of parts technology which Rogers is talking about. Rogers points out that mechanical conditioning equipment generally needs to be replaced long before the building shell its services. So to simply refurbish the patch center, the bulk of the HVAC system is set on the bridges between the A-frame masts above the roof. So what Rogers is trying to tell here is, in the structure, in any building, the mechanical and HVAC equipment will be needing servicing, will be needing replacement or repair more sooner than the building itself. Which means if you put the mechanical equipment deep inside the building, when the mechanical equipment is getting removed from the building, what happens is you disturb the entire functioning of the building. So Rogers simply did one brilliant thing. What he did was, he took out all the mechanical equipment, he placed it on the roof, so that it's very easy for anybody who wants to service the equipment. They can simply go up to the roof, service it, take it out if need be, and replace it easily. So the internal functioning of the building is intact, and nobody is questioning anything out of that. That is the genius in which Rogers designed it. This is the mechanical equipment which needs to be serviced, and clearly enough he has put it on top of the building. Very easy, simple and clever. These are the close-up photographs of what happens on the roof. Again, this is one section of the A-frame along with all the subordinate steel suspension cables which keeps the roof up. The concrete floor slab aside, the patch center's structure provides an armature from which the rest of the building's enclosure and services are hung. Set on 30-foot centers, its A-frame masts rise 45 foot above 25-foot wide portal frames that define the building's central circulation spine. Tension rods pinned at the top of the frames branch out to pick up 75-foot long roof beams at 4 points. The 4 points which they are talking about, 75-foot long beam which is carried at 4 points by the cables which run from this point. So look at what the street looks like with the service equipment above. This is the main entrance of the building from the inside and from the outside. Tension struts at the end of the beam stabilize the lightweight roof against uplift loads. Secondary beams supporting the 5-inch deep roof deck span between the main roof beams on 13-foot centers. The outermost facing beam is exposed on the building facade. Except for the local bending of the beams, gravity loads subject for the structure to essentially to only axial forces. This is a photograph from the side of the building where you can see clearly that the wall panels and the structure members are clearly differentiated, and this is how the light enters the building. Reflecting this and expressing the kit of parts concept, the most major structural connections are pinned through perforated gusset plates or clevises. With the addition of more A-frame masts and stays, the building is extendable on 30-foot modules. Horizontal wind load is distributed by the building's facade panels, acting as one-way slabs to the roof and ground panels. Wind is resisted at the upper level by steel roof deck, acting compositely with the beams beneath it as diaphragm. This is a building that clearly defines the skyline of the area behind. This is 3D view of the building, wherein you can clearly see how the structural elements are working. Here you can see the A-frame, this circular plate on top connecting to another circular plate at the midpoint level, which is again connected in turn to at 4 places where this beam is being lifted. So, each of these beams are lifted by these little plates, which are again lifted by this one single thing, which is supported by the A masts. Resting directly on the steel roof deck, 2 layers of rigid insulation covered with a built-up roofing membrane and gravel comprise the rooftop enclosure system. The upper layer of insulation is tapered for drainage. The facade is made of prefabricated pre-glaze 2 3/4 inch Carl wall panels set up in aluminum frames. 20% of the total panel area is clear glazed. The remainder is made up of a sandwich of translucent fiberglass insulation set between sheets of rigid fiberglass. This is a sketch explaining how the structural system acts in the building. Besides chiller, gas-fired boiler and drain pipes, all of building's air conditioning equipment and services are provided from above. Air handling units and primary supply and return ducts are cradled between the A-frame masts above the central spine skylights. Hot and cold water is supplied just below the roof level. To keep air moving to and fro the air handling units at the proper temperature, the main ducts outside the building are enclosed or insulated. Here is the detail of the AC system, where above this deck, this is the interior of the building and this is the exterior of the building. On the exterior of the building, the air duct is insulated. On the bottom portion it is not insulated, but on the top portion it is insulated. Branch supply and return ducts penetrate the roof in each 30-foot bay between mast and serve the 75-foot wide building sections to either side of the central spine with variable air volume fan assisted ducts. A perimeter hydronic heating system supplements the forced air supply in the winter, which makes sense given the facade's rather small R value. Separate foul wash basin lap drain lines are provided under the concrete floor slab. This is how the PA Technology Center looks like. This is a scale model which was made to understand how the building works. We shall directly move on to the Olympic Athletic Center of Athens, our next case study for the day. And this building was not designed by Richard Rogers as the previous 2 buildings were designed by Richard Rogers. This building was designed by a famous person called Santiago Calatrava. This architect is famous for his structural expressions, and any place across the globe, if you see any different building, there is a very good chance that the building was designed by Santiago Calatrava. The Olympic Athletic Center of Athens, OAKA, is a sports facility complex built in 1982 and refurbished for Athens 2004 Olympic Games under a design produced by Spanish architect Santiago Calatrava. The complex is an articulated building system inserted into the context of an existing sports center built in the 80s. This is how the building looks from the outside. The building was extensively renovated in time for the 2004 Summer Olympics. The roof was added on top of the sidelines and completed just in time for the opening of the games. The 2 giant arcs have a total span of 304 meters and a maximum height of 74 meters. These are the 2 buildings arcs that they are talking about. Look at some of the structures which Santiago Calatrava designed for this Athens Olympics. The sheer expression of steel. Look at how massive the structure looks and how great this structure looks in terms of expression. A total weight of 19,000 tons with 5,000 polycarbonate panels covering an area of 25,000 square meters. The west arc was assembled from 72 meters from its final position and the east 65 meters, both later slid into place. This is how the final building looks, with the arcs holding the roof of the building. This is again one of the interior photos of the building. The principal architectural interventions included a new roof for the Olympic Stadium, new roof for the velodrome, entrance plazas, canopies, a central plaza of the nations, tree-lined boulevards, a pair of arcade structure reminiscent of ancient agora. This is some of the structures that were installed in the Olympic Center for Athens. Design for a central Olympic icon and a sculptural nation's wall was also a part of this brief. The Olympic Stadium is covered with a roof of laminated glass composed of a pair of bent leaves capable of reflecting up to 90% of sunlight. The velodrome roof structure is composed of 45-meter high arches weighing 4,000 tons, from which glass and steel roof is hanging. 4 entrance plazas provide ceremonial access to the complex. Each entrance gate is roofed by vaulted steel canopy, which provides the public with a clear identifying element for the complex. When illuminated at night, these canopies serve as orientation devices. 2 are located on opposite ends, which runs between the Olympic Stadium and velodrome. This is a picture taken during the construction of the building, and these 2 arcs were constructed and then slid into place. The nation's wall is a tubular steel wall sculpture designed to move like a wave-like motion, creating a pleasing effect of light and shadow over the central circulation spine and the Plaza of Nations. The nation's walls can also serve as a giant video screen. This is the overall master plan of the entire athletic center Athens, in which in the existing center the buildings were designed. This is the big stadium which were designed, and these are the velodromes. The other areas and entrances and other canopies were all here. In addition, there are new warm-up areas for athletes, improvement of pedestrian bridges, connection to public transportation system, parking areas and bus terminals as well. All structures have been designed so that they can be prefabricated off site in large measure, reducing the need for on-site personnel and equipment and minimizing the interference along with other construction work which is happening on the existing buildings. This is a scale model of the building which shows the Olympic Stadium, the gallery through which people can move, and it shows all the other structures in the area. This is a section of the building where you can clearly see the 2 leaves which support the building. The stadium roof covers surface of 25,000 square meters like we mentioned earlier, and rise to a height of 60 meters. These are some of the sketches which Santiago Calatrava made to get the building right. This is another section when the arch is slid into place. By understanding this lecture, we should have come to an understanding of contemporary structural expression and stadium typology, factory typology buildings. We should have understood design philosophies of and concepts of famous architects or architects rather than architects, Richard Rogers and Santiago Calatrava. But with the learning that we have got so far from the lecture, you should be able to answer the following questions which are going to appear on your screen right now. Explain the Athens Olympic Stadium by explaining the structural genius of Calatrava. Explain the Fleet Guard and the way Richard Rogers has defined the industry setup in this kind of architecture. Explain the PAT Center building with reference to kit of parts technology and how it is used to solve the problems of the project. These are very interesting case studies, and I look forward to meeting you again with more interesting case studies on the other side of this lecture series. So, thank you so much.